I believe
in which
hydrogen
states
can
will
become
create
more
substances,
not
the ways by which we
because
live.
Today, we are joined by Dr. Lenny Klebanoff, a leading scientist at Sandia National Laboratories in Livermore, California. Dr. Klebanoff has spearheaded significant advancements in hydrogen fuel cell technology and previously directed the U.S. Department of Energy's Metal Hydride Center of Excellence. Dr. Klebanoff holds a PhD in physical chemistry from UC Berkeley, has 30 patents, and has authored over 130 scientific publications. He's also the editor of the book Hydrogen Storage Technology, Materials and Applications. Dr. Klebanoff, welcome.
Hi, Ernest. How are you today?
Quite all right. I'm very pleased that you're my guest today.
That's my pleasure.
Tell me, who is Lenny Klebanoff?
Well, that's a complicated question. There may not be a complete answer to that. It's still developing, maybe the answer, but I'm from Bethesda, Maryland originally, which is a Washington, D.C. suburb, and went to Bucknell University for chemistry. I actually got a combined degree program there, master's and bachelor's in chemistry. That was organic chemistry, is what I was studying back then. But I remember reading or trying to read these journals in physical chemistry, like Journal of Chemical Physics, Journal of Physical Chemistry, and not understanding a word of them. But I thought that they were dealing with very interesting topics and often very applied topics, which I kind of liked. So when I went to graduate school at Berkeley, I majored in physical chemistry, and in particular, I did my PhD with the late, great Professor David Shirley there, in working on surface science, surface magnetic properties, and using essentially photoelectron spectroscopy using synchrotron radiation. And this was a great education for me because surfaces are in everything, and it's very important in hydrogen storage materials. So after that, I did a postdoc at the National, what was then National Bureau of Standards, it's now NIST, National Institute of Standards and Technology, in electron spin polarization scattering. So I did spectroscopy using the spin aspects of electrons. And then I was a professor for 10 years at Lehigh University, created the technique of spin-resolved X-ray photoelectron spectroscopy, where you add spin analysis to X-ray, the normal X-ray photoemission study, which is also used a lot in hydrogen storage materials. But after 10 years away from my beloved Bay Area, I really missed the Bay Area. And also after 10 years of being a professor, I was a full professor and tenured, and I just felt like trying a different kind of job. It just, when I was 80 years old, I took the rocking chair test when I was sitting in the rocking chair and I was 80 years old. I just wanted to feel like I had the guts to try something different. So to make a long story short, I ended up being able to get a job here at Sandia National Labs in Livermore. And I was hired into what was called the EUV lithography project. This was a project to develop the technology for making basically a leap in terms of the line spacing of computer electronics. And EUV technology is now entered manufacturing and is really responsible for a lot of the really rapid developments in AI and so on. So, but during that time when I was doing really microelectronics research, there is a hydrogen program here. I was hearing about it. I was asked to work with Governor Schwarzenegger's team in the state of California to look at what a hydrogen highway could bring, what the benefits would be to the state of California and others. And that's really where I got interested in hydrogen. Back in 2003, as you mentioned, I was the director of the Metal Hydride Center of Excellence from 2006 to 2010, and I've been involved in hydrogen storage since then. But I've also created, in 2005, I created what's called our hydrogen market transformation program, where we look at possible applications for hydrogen and hydrogen fuel cells in different applications and see if there might be some benefit. So for example, I started this effort, which is still ongoing, working with Boeing. Boeing is interested in hydrogen uses in aircraft technology. So I've done a number of projects with Boeing and aviation. Looked at hydrogen applications in man-portable electronics, so that was a while ago, but more recently in construction equipment, in locomotive propulsion power, and most recently in maritime vessels, ships. So that work continues. My hydrogen storage work still continues, and it's been really a really fun experience. It's been really fun. It's been hard work, a lot of work, but it's also been really fun. So yeah, that's where I'm at right now.
Now I'm having a hard time where to start actually. So let's start from the beginning. Hydrogen in general. Uh, what's your feeling about it? How do you think it will look like in the future?
So I have to say, I'm not in favor of any particular molecule. It's like, it's like being in favor of a portion of the electromagnetic spectrum. Like I really like visible light, but I'm not so sure about infrared light. It just it kind of has that feel to me. So it's hydrogen as a molecule, and also Sandia. We don't at Sandia we don't advocate for anything. We just our primary purpose, I would say, or one of our greatest valued purposes, is to look at technical problems of importance to the U.S. And usually there are other problems if they're of benefit to other countries too, and take an unbiased look at them and provide feedback. I think that's probably our greatest currency. So I just want to say that. I also want to say that any of the views, like there's always a Department of Energy disclaimer that we have to put in all of our papers, where I call it the vote of confidence, where the Department of Energy says, uh, this was funded by the Department of Energy, but we don't necessarily agree with any of it. And any claims made are not necessarily those of the U.S. Government or Sandia. So I do have to say that anything I'll say here will be my own opinion, and they may or may not be shared by others here at Sandia, or even Sandia as a corporation or DOE. But I'll tell you what I think. So I think So having said all that, I think hydrogen's been there's a kind of a long history of looking at it, which I don't think people are very familiar with. It's been looked at as a transportation fuel since the 70s, really, where in this country there was an Arab oil embargo, and that really prompted the United States to look into energy sources for transportation that are not based on fossil fuel. So that's really one of a great benefit. Although at the time it wasn't an environmental benefit, it was really an energy security benefit that was really the focus there. But in the late 1990s and early 2000s, there was more of an environmental look because the awareness around greenhouse gas emissions became more prominent, uh, and the understanding that hydrogen doesn't have carbon in it. So it's not you don't have to be a great chemist to notice that. So hydrogen doesn't have carbon in it. So when you use hydrogen, either burning it or in a fuel cell, which we can talk about, it doesn't release CO2, which is good. Although you have to take a pretty hard look at how the hydrogen is made. It's very energy intensive to make it. So you have to look at how it's made to really know about the greenhouse gas benefits. It does enable high efficiency conversion devices, what I call like a fuel cell, I call an energy conversion device. Fuel cells can be in many operational aspects more efficient than gasoline engines and diesel engines, although very large diesel engines are pretty efficient, almost as efficient as fuel cells. So there's an efficiency benefit there. There's an energy security benefit there using hydrogen. But nature, Ernest, I don't know if you've ever noticed this, but sometimes nature is uncooperative. And so but every once in a while, nature will throw you a bone and say, okay, we'll make it easy for you on this one. But most of the time, nature's uncooperative. So there's some difficulties with using it, which we can talk about. But I think for applications where where it seems to be a good fit, I think it can be a very powerful, clean source of power, and that can be securely made and is reliable and especially safe. I've done a lot of work in understanding the safety properties of hydrogen, and I think it can be used very safely and enables high energy, high efficiency devices. But there's some things you have to really look at the application in a broad sense, and I think each application you have to look at individually, but look at it broadly, and we could talk more about what I mean there.
So basically, there is a place, but not as much as we expected, I read.
Well, I think it depends. So there's some applications. Like I don't think you'd ever want to use hydrogen fuel cell power for a pocket calculator.
For sure.
I don't think, I never like saying never, Arnes. I'm saying never to that. You're never going to use hydrogen fuel cell for a pocket calculator. But I've been involved in some applications where it seems to have some surprising benefits. So I'll tell you about one in particular. I've been doing work in looking into the feasibility of using hydrogen on ships. And shipping global shipping accounts for about 3% of greenhouse gas emissions, although most of that's like 90% of it is cargo ships, are really big ships. But you got to start somewhere. So we've been looking at ships. This has actually came about because, and this will be the topic of the webinar, which I'll be doing with you in
Yeah.
May. So
for everyone, yeah, just for everyone to know, we'll be doing the webinar on the topic of hydrogen storage, actually hydrogen usage in ships propulsion. So
yeah, I think so. It turns out that you might say, well, what are the competitors? Like, if you want clean energy technology, what are the competitors? One of the competitors is battery technology. And like I said, for a pocket calculator, for one of these, battery's going to win. It just will. I mean, it just makes sense, right? But we found something very interesting and a little surprising in powering ships, and that is we did a study a couple years ago, and I'm not going to preempt the webinar, so I'm going to shade it a little bit. But we did a comparison. In this case, it was a research vessel we were looking at, powering a research vessel either with, and it was in a hybrid sense where we were about a third of the installed power on the ship was either some kind of alternative energy like batteries or hydrogen, and the rest was diesel. So, but there's a reason we did that. But anyway, we found that for a large power application, in that case, it was about the fuel cell power plant was about 800 kilowatts. The amount of stored hydrogen the usable amount of hydrogen, which is different than what you can store, was about 730 kilograms. So it's a lot of hydrogen. It's a lot of energy. In that case, when you compared how much installed energy you could get on the boat compared to lithium-ion batteries, the amount of energy storage was usable energy storage was 9 times better for fuel cells, because batteries don't scale well in terms of weight and volume. So that's really a clear application where, like, when you compare it to a possible alternative technology, it's clearly better. But there are other things. There's all sorts of things to consider. And is hydrogen available? And is it can it be used safely? And it turns out you can use it safely on a boat. We've done a lot of work on that. So that's just one example, I think, where you just have to look at a specific application and see what the alternatives are, and then make a best decision. But I think certainly in that maritime example I just gave you, obscuring it somewhat, because I don't want to preempt the webinar, they could definitely have some applications. California, I think the fuel cell cars, California has about maybe 10,000, maybe 10 to 15,000 fuel cell cars. You can rent them. You can lease them, rather. You can lease them. You can buy them if you want. But there's some current challenges, just like there's a global inflation which has occurred. It's hit the hydrogen market. So hydrogen is pretty expensive right now. It's about $36 a kilogram here in California at a station. And, that's just increased in the past couple of years, like doubled. So So I'm not, Arnis, did you have something specific in mind when you were saying you don't think it's been as widespread you'd think? Or,
So I think it's just in the beginning and even like a testing phase. But let's go to the storage. What improvements are necessary in hydrogen storage technology to make it competitive with existing energy storage systems?
so you used a word called competitive. That's a good word. It's a fine word, actually, Arnes. I want to acknowledge you for using that word. But it turns out that the question of there's technically competitive, there's economically competitive. So you really have to look at it broadly. And so there's several ways of storing hydrogen. There's sort of three principal ways. You can store it as a liquid hydrogen. That's been done for decades and decades. It's been done in the United States since the 1960s. The United States is pretty far ahead, I'd say, of other areas of the world in terms of liquid hydrogen technology, just because of the American space program. So liquid hydrogen was used to propel the Apollo 11 astronauts to the moon and the Saturn V launch vehicles because it's so light. So there's liquid storage, there's high pressure gas storage, where usually you want to get as much hydrogen, which is normally a gas, into as much, you want to cram it into as much space as you can. So there's high pressure storage. Both the liquid hydrogen storage and the high pressure gas storage are, I would say, fairly mature technologies. There's certainly, I think those industries deserve a lot of credit for making storage products that work well. The cryogenic tanks used for liquid hydrogen storage are complicated, highly engineered devices which work very well. I think the high pressure tank industry deserves a lot of credit for making a product that works well. Both type 3 tanks, which are the ones where you have an aluminum liner surrounded by composite overwrap, or the plastic, the ones with the plastic liner, the so-called type 4 tanks. And how you use those, even with those, the question of competitive really, you have to understand how they're used and what restrictions on how they're used might be in place. So there's those two. And then the third one is solid state hydrogen. Well, what I would call material storage, which can in principle be liquids, liquid compounds that carry hydrogen. Those are called liquid organic hydrogen carriers, or solid state materials. These are like powders typically that can store hydrogen and release it. So before looking at any one of those two particularly, Arnis, I just wanted to explain why I said that you have to look at the broader picture of how these things are used. And really competitive will come from the end user. What an end user wants, they have all the power and say in this, right?
Exactly. Probably starting with safety, yeah.
Yeah, safety, for sure. So I just wanted to highlight a few things. I mean, I'm guessing the audience knows maybe a fair amount about kind of how hydrogen is stored, but they may not be so familiar with how it's used. So there are restrictions from the end user's perspective. There are some restrictions that you have to take into account, which will help an end user determine what technology is more competitive than another. I want to give you some examples that maybe most people don't think about. If you're using a high pressure tank, right? Let's say it's 350 bar tank or a 700 bar tank of hydrogen. Ultimately, if you're using that in some application, you have to ask yourself, how is it going to get filled? And the traditional way of filling this, especially like if you have a project at some location, is there's a hydrogen trailer that comes by and has, usually they carry 15 tanks of 350 bar. Usually it's like 350 bar, maybe 450 bar tanks of hydrogen, and you do a cascade fill into your high pressure tank, right? And usually there's a lot more hydrogen on the trailer than you're trying to fill in most cases, and so no problem from an end user, good to go. right? There's a perfectly reasonable way to do it. But what if you're wanting to fill, if you have some high pressure tanks in which there's a significant volume, you start to wonder, well, how much hydrogen can I get transferred from the trailer into my tanks? And if you're starting to have a significant amount of volume, like maybe hundreds of kilograms of hydrogen, because these trailers do cascade filling, right? They open up one tank at a time, let the pressure equalize, then close that, open up the next tank and let the pressure equalize. It's a rather inefficient way of transferring hydrogen. And maybe you can only transfer 60% of the hydrogen which is on that trailer into your tank, depending on the relative sizes. So that might get into the question of how many trailers do I need to fill my application? So that's the reason I say that, RNS, is that's a consideration with how these things are used, which maybe people don't think about. You think, okay, no problem, I can fill an 8 kilogram capacity, 350 bar tank, no problem, right? But as the storage capacities get more, how you actually use these tanks come into play. And that's an issue of competitiveness, because if you're looking at comparing, say, high pressure hydrogen to liquid hydrogen storage, where when you transfer liquid hydrogen into a liquid hydrogen storage tank, you can pretty much fill it as much as you want because they're pressure filled, right? So in that case, well, you can get more liquid hydrogen into a given tank because of the specifics of how it's done. But then there's some regulatory issues which people don't know about. And I want to highlight this because I don't think people would probably know about this. So when you use in a liquid, I've done a lot of work looking at using liquid hydrogen tanks for ships, right? So it turns out there's some maritime regulations, and they also apply to liquid natural gas, where there are restrictions on how filled up you can fill a liquid hydrogen tank, or how filled up you can fill a liquid natural gas tank. They don't let you fill it all the way up, and there's a very good reason for that. And the reason has to do with when you're filling a liquid hydrogen tank. It's a technical detail, but I'll explain it. When you're filling a liquid hydrogen tank, you have to avoid getting to a condition where the tank is nearly full, because with heat ingress into the liquid hydrogen tank, you can start to get more evaporation. You get more higher pressure in the headspace of the tank. The headspace allows you to get to maintain the liquid in the liquid state, but at higher temperatures. So the temperature of the liquid will expand. The temperature will get higher. The liquid will expand, and you can get to a point, even during a filling operation, where the liquid, because there's heat ingress, the liquid is expanding, it's at higher pressure, which allows you to maintain a liquid state at higher temperatures. You can get to a point where it's 100% full, and then you can have a severe overpressure event. So in maritime, they only let you fill these tanks 74% full.
Okay.
So that impacts. So is liquid hydrogen now competitive? I just took a 25% hit, 26% hit. So the thing around competitiveness, which I wanted to convey to you and to the audience, is that you have to have a much broader view of how these things are used, or maybe constrained by regulations. Because in comparing hydrogen to some other technology, which maybe because of its physical attributes don't have similar restrictions, it will really affect what you think is competitive or not. And these issues are coming up, for example, in vessel design, hydrogen vessel design, where they're planning to use considerable amounts of hydrogen. But ultimately, so I just wanted to highlight those things. You have to have a broader view of competition, I think, and other candidate fuels have their own issues, right? But generally, the biggest difficulty with using hydrogen compared to like diesel fuel is just its volumetric density. Like liquid hydrogen per energy stored, per lower heating value stored, is 4 times larger than diesel fuel. And that fact rears its ugly head in all kinds of applications where you're volumetrically constrained in some sense. And that can come into effect it did not come into effect in aeronautics, like in rocketry, because weight reigns supreme in that. And per amount of energy stored, hydrogen is like about 3 times lighter than any liquid fuel, any like liquid hydrocarbon fuel. So again, in that case, it's highly competitive because of its weight advantage. In applications which aren't so weight sensitive, where there's volumetric constraints, there could be some real challenges. So it really just depends on the application, I think, Arnes, and looking at that application broadly, not just what's the storage density of hydrogen, what's the density of hydrogen in liquid hydrogen at 71 grams per liter. What's the density of hydrogen in 700 bar hydrogen? Well, the density of the gas is 40 grams per liter. Or at 350 bar, it's 23.8 grams per liter. It's not just that number. It has to be looked at broadly. So that's the most important thing I wanted to convey. And in solid state storage, there's, which we can talk more about that. There's also similar types of constraints with how you use it. But there can be some real advantages, which may help you in some cases overcome some regulatory requirements. And we can talk more about that.
Let's touch on the embrittlement and permeation, and on the lifetime of let's say tanks and pipelines.
Yeah, this is I give a hydrogen safety seminar to various organizations. For example, I do a lot of work with the United States Coast Guard. I give them to other organizations, and I like to talk about embrittlement and permeation. The permeation one I think is misused by. There are a lot of concerns about permeation rates with hydrogen, which sounds horrible. So I'd like to just take a moment to explain what we're talking about here, what the technical thing is. So if you have a tube which has hydrogen in it, say it's room temperature hydrogen, say it's pressurized hydrogen, hydrogen molecules will dissociate on that. It's typically a metal tube. Like it's a metal tube we're talking about. Hydrogen molecules will dissociate on most metal surfaces, and the atoms will penetrate into the metal. And it's possible for the hydrogen atoms to diffuse all the way to the other side of the wall, of the tube wall, reassemble as hydrogen molecules and desorb.
Gosh.
That sounds horrible.
Yeah.
Doesn't that sound horrible? Like, how could you ever contain this stuff? Well, it turns out that in metals, the permeation is so slow. And I'll give you an example. So here's an example. It turns out Sandia's done a fair amount of work in the permeation of hydrogen in metals. And so if you took I happen to have the numbers from a specific example, why I won't go into, but if you take 1,200 kilograms of liquid hydrogen, say, and you gasify it, okay, and permeation is actually, this process I described is thermally activated, so it's worse at higher temperatures. It's almost non-existent at cryogenic temperatures. It's virtually non-existent. But anyway, you heat it up to room temperature so you can turn on permeation. It's also pressure driven. So the higher the pressure it is, the more this permeation can happen. So you pressurize this thing to, like, say 150 psi. So you take 1,200 kilograms of liquid hydrogen, vaporize it, compress it to 150 psi, and then you enclose it. And it turns out that the radius of that, if you may imagine taking a spherical volume holding that pressurized room temperature hydrogen, it's a 7-meter radius sphere. So it's kind of a big sphere, but you've compressed it, you've given permeation the conditions it wants. It's room temperature hydrogen, it's pressurized. The amount of time, and you can calculate how long it takes permeation to go through that material. So imagine the hydrogen is permeating through the metal shell, say it's a 1/16 of an inch thick of stainless steel. You collect all the hydrogen which is coming through that big sphere, and let's say you feed it into a phone booth. Now, Ernest, you don't look so young that you've never been in a phone booth. I'm guessing, have you been in a phone booth?
Definitely.
Okay, so some of our younger students may have no idea what we're talking about. But a phone booth, if you imagine taking all that hydrogen which is permeating through that shell and feeding it into a phone booth, it would take 60 years to get to the lower flammability limit. So it's a vanish. And if assuming you use the right materials for hydrogen, which is an important thing, you're not using plastic tubing, you know, silicone tubing or rubber tubing for the stuff which everybody knows. Permeation through plumbing, through tank materials is vanishingly small. In fact, typically the hydrogen which people are breathing out, because we're both breathing out hydrogen right now. I don't know if you knew that. It's produced by respiration at a few ppm. The collection of 150 people just breathing out hydrogen would be a greater source of hydrogen leak than by orders and orders of magnitude than permeation. So permeation, choose the right materials. You have to use copper or aluminum tubing if you want it, but typically people use stainless steel, 304 stainless steel or 316 stainless steel. And the permeation problem is non-existent as a safety issue, just because it's vanishingly small. It's kind of of interest to material science, because people in material science like to study certain things, but as a safety issue, assuming you're using the right materials, and we know what materials to use, 304, 316 stainless steel, it's not a safety issue in the slightest. Embrittlement. So does that make sense, Artis, around permeation?
Yeah.
It's
spot on. Yeah.
If people raise permeation in some kind of safety discussion about hydrogen, it's because they're not familiar with the science of it, or really how people have been using hydrogen. You have to make the right material choice. And I want to emphasize this, but people shouldn't be scared of materials choices. I mean, we do it all the time. Like in your house, Arnes, you have copper wiring. Yeah. There's a reason you use copper wiring. It doesn't heat up when you pass electricity through it. If you have iron wiring in your house, get out of your house.
Yeah.
Iron will heat up a lot when you pass electricity through it. So you make a materials choice, just like, copper isn't good for some things. Like, Arnes, if you have a friend who for Christmas gives you a toaster with copper wires as the heating element, that person's not your friend. That's not your friend. So question that friendship if that ever happens to you.
Definitely, but we will go to the materials question for sure. But let's go back to embrittlement.
But the embrittlement, just to say about embrittlement, again, it comes down to a material choice. 304, 316 materials, the so-called austenitic steel materials are very robust against hydrogen embrittlement. Copper does not suffer hydrogen embrittlement. Aluminum doesn't suffer hydrogen embrittlement. So you have to make the right materials choice. When there's been safety issues around embrittlement, typically, and accidents which have been caused by something that could be traced to hydrogen embrittlement, at least in hydrogen service, like the plumbing and using hydrogen directly, is because somebody made a mistake in the materials choice. There was a part of a valve that wasn't rated for hydrogen service, or they used a component that wasn't rated at all for hydrogen service, and therefore didn't have this materials choice built into it. So that's all about using hydrogen. Now, hydrogen embrittlement does come into play in some like civil engineering issues, like in bridge structures, which can, when exposed to water, and there can be some hydrogen embrittlement in those cases. But in what we're talking about, like hydrogen uses in transportation, you have to make the right materials choice. But once you do, you're pretty good to go.
So what are the most promising materials or technologies for hydrogen storage that your research has identified?
So again, it always will kind of depend on the application and looking at that broadly, like I said. But the hydrogen storage materials, I'll tell you, just start by saying that why people are interested in them. So if you look at the density of hydrogen in liquid hydrogen, I mentioned before, it's 71 grams per liter. The density of hydrogen in 700 bar hydrogen gas is 40 grams per liter. The density of hydrogen in the compound ALH3, aluminum trihydride, is 149 grams per liter. It's like, that's a lot of hydrogen. There's a lot of hydrogen in that material. So people are interested in material storage primarily for the hopes that it can offer greater volumetric density, because aluminum ALH3 we could talk more about its properties. 149 grams per liter, it's more than twice that of liquid density. It's pretty amazing. So there's an interest there. And then the other interest is in low pressure operation. In principle, the whole idea is that you can have a metal, like say a metal hydride, which is a compound that has hydrogen in it. If you heat it up, it releases it, and then you can hopefully get the hydrogen back on in a reversible sense. The idea is that if you could do that at low pressure or close to either your room temperature or where the temperature of a fuel cell operates, you can avoid the trouble of having to liquefy hydrogen, and you can avoid, which comes with energy costs. Takes about, whatever the lower heating value of liquid hydrogen you have, it takes about 30% of that energy to liquefy it. So you avoid that trouble. And with high pressure, it's the energy of compression is something you'd like to avoid. It's like 10%, I think, for 350 bar, maybe 15% for 700, or 15 to 20%. It's a somewhat smaller penalty. So the idea is you could avoid those energy penalties. And so that's why people are interested in solid state storage, better volumetric storage, and lower pressure operation, which might help you avoid things. It might improve safety. Although I have to say, high pressure tanks are pretty good, RNS. I mean, that industry has done a great job making those tanks safe. So what materials are traditionally looked at? So really in the 80s, the people working in this field, I think, did a great job, 70s and 80s, because if you don't care about weight, the weight of it, there's some superb hydrogen storage materials that can release hydrogen exactly the way you want to release it, and reabsorb it exactly the way you want to release it, or the way you want to absorb it, and they work beautifully. But they're typically very heavy. Those are called interstitial metal hydrides. And another group is really, which came with people's interest in using them from automobiles, is what I saw called complex metal hydrides, where they're more molecular looking things, like sodium alanate is an example one, sodium AlH4 is an example of that. Magnesium borohydride is an example of that, magnesium with BH4, 2 units of BH4 attached to it. If you just notice from the chemical labels, those things have a lot of hydrogen in them. NaAlH4, sodium aluminum hydride, that's 4. There's more hydrogen atoms in it than any of the other atoms. Magnesium borohydride has a lot of hydrogen in it. But there's always a problem, and this is where I mentioned that nature is not cooperative. There's something wrong with trying to do this, and I call it the 7 deadly sins of hydrogen storage materials. So there's 7 deadly sins, RNS, in life. Not that I'm an expert in the life sins, but there's greed, envy, lust. There's being slothful. That's just 4. There's some others. But the 7 deadly sins for materials hydrogen storage is they're too heavy. They don't release hydrogen fast enough for some application like a car. You can't reabsorb hydrogen fast enough, like in 5 minutes going to a hydrogen fueling station. They hold on to the hydrogen too tightly. So the prior 2 were bad kinetic problems. They don't release hydrogen fast enough, and they don't reabsorb fast enough. Those are kinetic problems. There could be a thermodynamic problem. They hold on to the hydrogen too tightly. You can't get the hydrogen off the thing. They can be too expensive. They can release stuff other than hydrogen. You really, when I have a hydrogen storage materials release it, you just want it to release hydrogen. I don't know how many I've gotten up to, but that's a lot. I've gotten pretty deep into the deadly sins. Oh, they don't cycle well. Maybe they don't cycle well. They don't reproducibly cycle. So when thinking about like what's a promising material, you have to look at it from that perspective of the 7 deadly sins of hydrogen storage. So, and I think you asked like what's promising. So I'll just sort of tell you generally how I'm seeing it and what things we've been working on and why we're working on them. And I'm working on them. So And it kind of gets back to your competition question, and that is, what is it for the hydrogen storage material? What is it you're trying to beat?
Yeah.
And let's suppose you're
There's
trying
no
to.
one. There's no one size fits all. This
Yeah.
is
So there's
yeah.
no one size fits all, but you have to do better than high pressure gas, I think. But the question of are you doing better than high pressure gas really depends on the limitations of high pressure gas that I talked about, like how can you refuel it, and there's some limitations on hydrogen storage materials. But let me just tell you about a couple materials. So thank you for bearing with me while I give that kind of long introduction. But when viewed against the seven deadly sins of hydrogen storage, a material which I think has some promise is this. It's an amide based material. It's lithium amide. It's a system lithium amide plus 2 lithium hydride, or lithium amide combined with magnesium hydride. And I'll tell you why. I'm personally interested in those. I'm of the opinion that because of the difficulties of using a solid state hydrogen storage material, it's going to, in whatever application you're targeting, it's going to have to be a lot better than high pressure gas. Whatever a lot better means, it's going to have to be a lot better because of the system's overhead of having to use a hydrogen storage material. That is, you have to heat it up to get the hydrogen off. You have to take care of heat being released from the material when you're putting the hydrogen back on. Those are engineering complications which you don't have in a high pressure tank. So whatever application, in my opinion, this is my personal opinion, it's going to have to be a lot better than high pressure gas. So what does that mean? There's a couple. So that primarily means higher, I would say, capacity, higher gravimetric capacity and volumetric capacity. So there's 2 materials that I think are very interesting, and I'll tell you why. The amides are interesting to me because both the system LiNH2, which is lithium amide, plus 2 lithium hydride, that's kind of a classic amide hydrogen storage system. One of the problems with that material, one of the problems in solid state hydrogen storage is the creation of intermediates. That is, when you're releasing hydrogen, you create intermediates, which you don't want. They slow things down kinetically. They're tying up hydrogen, and even in rehydrogenating, formation of intermediates is bad. You don't get back to the starting point. The amides are interesting because they're fairly high capacity materials, depending on which one you look at. It's like 5 to 8 weight% materials, which is the ratio of the amount of hydrogen in it compared to the total amount of material you have them in terms of mass. And the reason, I'll tell you, Ernest, why I'm interested in this material. The lithium amide, lithium hydride material has a problem in that you can't get, it's typical of the amides, by the way, you can't get all the hydrogen off. LiNH2 has nice 2 molecules sitting there, 2 equivalents of hydrogen sitting there, but you can't get them all off in the bulk because it stops at an imide, LiNH, Li2NH. So it stops, you can only get one of them off for thermodynamic reasons. So, but we did a study back in 2017, which I think gave us a view of what might be possible. And here's what we did. We took some lithium metal, and why I did this work with Vitaly Stavala at Sandia. We took some lithium metal and dissolved it in ammonia, liquid ammonia. And lithium metal dissolves in liquid ammonia, like all the alkali metals do. And then we put in that mixture some nanoporous carbon with like a 3 nanometer pocket size. And what we found, to make a long story short, is that we were able to get into that pocket after cycling in hydrogen a few times in nanoconfined equivalent of lithium amide plus 2 lithium hydride. The bulk system, but in a nanoconfined material, 3 nanometer pocket. And what we found that when we cycled that material was that we were able to liberate all of the hydrogen that was in the LiNH2. And we were able to not see at all. In fact, we looked hard for it. We never found this intermediate LiNH, which is so problematic. And we think the reason for that, we were collaborating with some theorists over at Lawrence Livermore across the street, was that it turns out that for that particle size, the energetics of developing different phase boundaries, the interface energies associated with these conversions, makes the production of the imide NH very unfavorable. So why am I interested in this? If we could find a way to avoid intermediates in these hydrogen storage materials, and the amides in this one example, they've shown us that we could do it, where we can eliminate an intermediate and get all of the hydrogen out of this material, that would be a great development in hydrogen storage materials. It still desorbs hydrogen at too high a temperature, around 250. So it's a little, for light duty vehicles, it feels a little too high, but it's still, I think it'd be a great development. And we've seen something similar in the borohydride materials. So magnesium borohydride is MgBH4 taken twice. And that when you can get all the hydrogen out of it, you go to magnesium diboride, MgB2. And what we found in some recent work, this is very recent work, was that if you add some lithium hydride to that material, you can get magnesium diboride to rehydrogenate all the way back to magnesium borohydride without any intermediates. And also do it 100 degrees at 100 degrees lower temperature than the bulk material without any additives at all. So I think in these classes of materials, amides and borohydrides, where there's a chance to really get what I would call a home run, where the capacities are much higher than in other systems, particularly in the borohydrides. And we've seen in these two experiments a way to avoid intermediates. If we could understand that better, I think these materials have some real promise, and that's something I'm personally interested in pursuing. So those are I'd say those are two class of materials that I'm pretty interested in. But again, the 7 deadly sins raise their head, and that's why the hydrogen storage problem has been so difficult. It sounds actually easy. Well, you just make a sponge that can soak up hydrogen and release it, and get it back on. But when you put the requirements on it around these 7 issues of cyclability, of kinetics, of thermodynamics, of capacity, and so on and so forth, it gets hard. But those are the two class materials which I think, for those specific reasons, in the bypassing of intermediates is a great future direction for hydrogen storage research, and really understanding why it happens.
How do safety concerns shape the development of these solutions?
So, are you talking about solid state storage materials specifically, or more broadly hydrogen storage in liquid and high pressure form?
Let's say more broadly.
So so it's a very interesting question you asked, and it's something I'm encountering right now, because I'm not going to preempt the webinar, but we're working on some hydrogen vessels designs, and actually ones which are going to be built. The liquid, there's some safety concerns, which I think in the case of hydrogen can be not well based in science and maybe overly conservative. And I'll give you an example of one. Let's talk about liquid hydrogen. So in liquid hydrogen, there are no fully agreed to or developed hydrogen safety regulations for using hydrogen on a boat. Since they're developing now because of the work I've done with the Coast Guard and U.S. Coast Guard and understanding hydrogen and try to figure out what makes sense. But there's a lot of regulations around the use of LNG. So the way people in the maritime do it is if you're going to use a liquid hydrogen tank on a boat, you pretty much have to get through the regulations around LNG, which is a perfectly reasonable thing to do because the fuels are very similar. But one of the things that a liquid hydrogen tank on a boat has to do is to be able to hold its charge for 15 days without venting. And so you can ask why that is. You can ask, first of all, why is it 15 and not 14 days? But I don't know, it's 15 days. So you have to be able to hold that charge without venting for 15 days. So in our designing of liquid hydrogen tanks for that application, that's the thing. You got to meet that deadlines, meet that criterion. So how does that affect the design of liquid hydrogen tanks? you can kind of sort of not change the design at all and just put less hydrogen in there, because the less hydrogen you have in the limit of 3 molecules of hydrogen, they'll just evaporate, and you never get to the pressure limit, which is usually 150 psi for a liquid hydrogen tank for venting. Well, that's a little variable, but the design of the tank, and that's a safety-driven requirement, because they just don't want hydrogen leaking from these tanks, coming out from these tanks. So it can affect the safety for liquids. I'd say it's mostly affecting the hold time, and that can go to in an operational sense how much you fill it. But in the design of the tanks, how thick is the inner liner? What's the level of insulation? You can make choices around that design, which gets that 15 days. And liquid helium tanks, which are even better insulated than liquid hydrogen tanks, that technology actually exists. The question is, do you implement it for liquid hydrogen? So that's an example for liquid hydrogen. So that's for where safety is kind of driving the design. For high pressure tanks, there's a safety issue, and that is when you fill a high pressure hydrogen tank with hydrogen, it heats up. That is, the gas, when you're squishing and squishing and squishing hydrogen into a high pressure tank, the gas heats up. And the design of those tanks has had to respond to that phenomenon of tank heating. And if you have a steel tank, like, you don't care about weight, you just have like a carbon steel tank, you kind of don't care how hot it gets, or a stainless steel tank. But usually you like tanks that are lighter. So type 3 tanks, which are an aluminum tank, it's an aluminum inner liner but reinforced with a carbon fiber overwrap. Those tanks are designed because such that they can handle that temperature increase, and the limit. So the type of epoxy you use in the carbon fiber overwrap, it turns out, is thermally limited. And this compression heating, that whenever you fill a tank, you have to make sure that carbon epoxy is compatible with the heating you're going to see in your application. Now, if you can wait 2 days to fill a high pressure tank, no problem, right? You can just fill it really slowly. But nobody wants to wait 2 days. They want to fill these things as fast as possible. So there's been some very nice developments, and I know the people at Luxfer used to be. There was another company name they bought, but anyway, they recently developed a high temperature epoxy such that the type 3 tanks, they call them high temperature tanks, can now take up to, which are light, so they're useful, can take up to 120 centigrade of heating. So, and that was a recent breakthrough in terms of the epoxies used in the composite overwrap. This temperature dependent heating of high pressure tanks is an issue for type 4 tanks. Those are the ones with a plastic inner liner. They're even lighter weight than the type 3 tanks. That's why people especially like them, I think, because they're lighter. But the epoxy used in the composite overwrap has to be able to take that temperature. And the current limit, it's a safety-driven design, because what happens is if that epoxy fails from the way you're using it and filling it, the tank will fail. And you don't want a high-pressure tank to fail like that. So the current temperature limit for filling a type 4 tank is 82 degrees centigrade. So that's an explicit safety design with how those tanks are being designed. Now, in metal hydride storage, it's kind of different. There are safety issues. Like, for example, all of the metal hydrides are very air sensitive. They react with moisture in the air. More typically, it's moisture. They're less reactive to molecular oxygen. That double bond in oxygen makes oxygen less reactive than water. You don't want to expose these materials to a leak such that you can have air ingress, because you can get a fire. That's pretty easy to defend against. For the functioning of the tank, you don't want it exposed to air. So that'd be an example. The pressure requirements are less. I'd say the safety issues are in a functioning metal hydride tank will be around heat dissipation when you're refueling it, because like in an automobile, if you imagine using a metal hydride tank for an automobile, and there's 5 kilograms of hydrogen typically in a fuel cell vehicle. You use that 5 kilograms over the course of a week. So you're slowly heating the bed. It's releasing hydrogen over, intermittently, maybe you're driving somewhere, but cars are mostly parked. They're not used very much. But when you're refueling these things, you're having to dissipate a tremendous amount of heat in a short time. So if you imagine trying to fill a metal hydride tank in 5 minutes, the amount of power, the heat rejection power that you're trying to dissipate can be a megawatt or more. There's going to be safety concerns around that. So there's some very important work currently going on at NREL. Prior to this project I'm about to tell you about, the only really fully operational metal hydride tank that would be suitable for a car's drive cycle was built at Sandia as a GM-funded project. And by the way, we'll have a bibliography of any paper I reference and what I'm talking about. So this is a paper I'll reference. We'll put in the bibliography RNS. And that is, it was a 4 kilogram tank, and it was quite an effort to reject the heat from that thing if you're refilling it. So the project at NREL I mentioned is they're going to be fully exercising a 500 kilogram tank, but that's the amount of hydrogen stored. It's not the mass of hydrogen. It's not the total mass of the tank. It's 500 kilograms of hydrogen in that tank, and they're going to be exercising that. It's going to be a titanium iron material, but I think from a hydrogen safety point of view, the heat rejection during fueling, if you're really doing it in 5 minutes, is going to be a safety issue, and we'll have to make sure that all of the materials are compatible with that heat rejection. That's going to be a major engineering challenge. I think it can be done, but it's going to be a safety issue.
So for everybody watching this, we'll have the links to the research papers in the description, so you'll be able to look at it, download. What are the trade-offs between high-pressure gaseous storage, cryogenic storage, and solid-state hydrogen storage?
So I've mentioned some of them previously. And it gets into, like, you can't think of it narrowly, you have to think of it broadly, like how these things are going to be used and what's the regulatory space around them. So I mentioned already, and again, I'm going to take an end user view of it because it's the end user that's going to drive the adoption, I think. The end user cares about price, for example, but the end user doesn't care that, at least me as an end user, I'll speak for myself, and if I'm an end user, I don't care that it takes 10% of the lower heating value of hydrogen to compress it to 350 bar. I don't care about that. But it's kind of in an academic sense, it's a concern. But as a end user, I don't care about that. I do care about if it takes a lot more money for me to get the hydrogen because of that. I equally don't care that the liquid hydrogen liquefaction energy costs 30%, to liquefy it costs 30% of the lower heating value. I don't care about that as an end user, although if it makes it more expensive, I start caring. So what I care about as an end user, how much hydrogen can I get and store in a given space and be able to use it in the regulatory environment that I find myself in. So that's how I'm going to think. That's how I'll try to answer your question, Ernest. So some of the trade-offs we've already mentioned in liquid hydrogen storage. One of the trade-offs, if you're in Europe, is the availability. So it's not very available in Europe. In fact, there's a liquid hydrogen ferry, which I'll describe more in the webinar, operational in Norway. It's the first liquid hydrogen ferry in the world. Do you know where they get their hydrogen from? Germany. They get it trucked in from Germany. So availability of liquid, like one of the trade-offs for liquid hydrogen is availability if you're in Europe. But if you're in the United States, you can get it pretty easily. It's pretty available. So availability is a trade-off for liquid. And I already mentioned the fact that there are these safety-based regulations on how much you can fill it. But the other thing, too, I forgot to mention with liquid hydrogen storage is you have to leave some liquid hydrogen in there when you want to refill it. because you want to keep the tank cold, for example. You want to keep the tank cold so that when you're refilling it, you don't want to try to refill a room temperature liquid hydrogen tank because you're just wasting a lot of hydrogen and cooling it down, and that's money. So one of the trade-offs is not only the fill limit for liquid hydrogen tanks, which is to prevent this overfill condition, but the fact that you have to leave some in there just to use the tank, to cool down the tank. So fill limit could be 74% full. The fill limit could be 5%. The residual amount you have to leave in there is 5%. That means only 69% of the available space can be used. That's a trade-off. Okay. What about for high pressure storage? Well, but the benefit of using liquid hydrogen is that the volumetric density is better. So that's a positive feature. The volumetric density is better. The refueling time can be quick. You can very efficiently fill a liquid hydrogen tank from a trailer without any, leaving any in the trailer if you don't want. So there's some real benefits. So I mentioned initially the negative ones, but I should be a little more optimistic. The positive ones are real. That it's it's the best way to store a lot of hydrogen in a given space is liquid. That's just the volumetric benefit. There's also some weight benefits too, having to do with the lightness of the fuel. Anyway, now let's go to high pressure gas. I've already mentioned that because high pressure tanks are filled by usually cascade filling. If you don't happen to have a compressor on your car or on your boat, right, you're stuck with cascade filling because trailers don't have compressors for the end customer usually. There's a negative part of the trade-off is that you may, depending on how much hydrogen you're trying to store in a high pressure tank, you may require more hydrogen trailers than you think because you can only get 60% of hydrogen off of a trailer. Another area is in the time it takes to refuel them. You have to observe the thermal limits. For a Type 4 tank, it's 82 degrees. You can't surpass that. And that means you have to be careful about slowing down the refill, or you have to pre-cool the hydrogen. So that's a trade-off. If you have for automobiles, usually there's something called the J2601 protocol where the hydrogen is pre-cooled so that you can fill a tank in 5 minutes. But since the hydrogen is already pre-cooled, the compression heating that takes place starts from a lower level, and so you can still fill it in 5 minutes. So that's a concern around high pressure tanks, usually Type 3 or Type 4 tanks. That really is a unique trade-off associated with high pressure storage. The benefit is that high pressure storage, the high room temperature, high pressure gas is more available than liquid gas. Liquid hydrogen I'd say it's more available. So that's a benefit. The tank technology is extremely mature and well done. And so it's again, I like to acknowledge industries for the good work they do. The people who made those design, the industry that really made those tanks have done a really nice job with making them safe. Someone could look at the high pressure tank and be concerned about safety. 350 bar is roughly 5,000 psi. So a car pressure, the pressure of air in your tires is like 35 psi. So it's 100 times more pressure in a tank, and 100 is a big factor. 100's a big factor on this. It's the difference between walking and flying. That's a factor of 100. Yeah. So the trade-off can be, if you're very concerned about pressure, the fact that you have a very high pressure, 10,000 psi or 700 bar in some of the light-duty vehicles. But my technical experience is that those tanks function very well and are safe. But someone may have a concern about high pressure. And also the availability of 700 bar pressure, by the way, is not that great. The trailers are limited to about 450 bar. So if you really want 700, if you want to go up in pressure to 700 bar, in a mobile application, it's pretty hard. The hydrogen stations can do that. Trailers, I don't think, can do that yet. So those are some of the trade-offs. But going down to the materials, the trade-offs are you're better volumetrically. Again, you have to really take a hard look at the support equipment, because I mentioned the thermal issues, the thermal management issues. You have to include the balance of plant, the thermal management equipment, and so on. That has to figure into the volumetric efficiency. Lower pressure can be a real benefit. You can potentially fuel these things with low pressure hydrogen, and you never have high pressure hydrogen in them, but it's going to be the downside of the materials from a trade-off point of view is the thermal management. It's a pain, Arnaz, to have to put these metal hydride materials in tanks with cooling coils or cooling rods, and you're worrying about providing the thermal conductivity of the material. Can you heat it up enough to be able to get the kinetics right? It's a much more complicated engineering problem, metal hydride tank, which is a significant drawback. I'm not saying it can't be achieved, but it's a drawback. And again, I mentioned the much more serious thermal management of refueling the metal hydride, where you're trying to get kilojoules of energy out in 5 minutes, where you can get into megawatts of power dissipation. So, but again, there might be some applications where they're willing to put up with that. So again, the trade-offs have to be viewed against the application and against taking a full view of the system penalties with using these things. And the DOE was very good about identifying that whenever you look at, like for a metal hydride or a solid state storage, you have to look at the system gravimetric capacity or the system volumetric capacity, because that's all the other equipment that it takes to get it to use. But even beyond that, you have beyond the what I would call system hardware points of view, there's the how you use it in the real world view, which is what you also have to take into account. So there are trade-offs all over the place for everything, as far as I can tell. But you have to be thinking about it broadly.
Let's go to the vessels. What safety and efficiency challenges exist with hydrogen-powered vessels?
So let's see. By the way, Arnaz, I wanted to show you something. So this is a mug I got from Munich, Germany. I don't know if you can see this. Can you see that?
Yeah.
So I made a very important archaeological discovery. I found that the very first hydrogen trailers were in Munich. You see that right there?
Yeah.
The horse-drawn trailer with what I'm only presuming are hydrogen tanks.
It looks like a beer to me.
So anyway, let's see. So for boats, could you repeat your question again, Arnaz? For the
hydrogen safety concerns in vessels.
Yeah, so I was distracted by my cup. Sorry about that. I touched on it briefly, but let me expand on it. There's no hydrogen regulations fully agreed to for using hydrogen on a boat. So what's done typically is there's an organization called the International Maritime Organization, IMO, which has developed kind of guidelines for using natural. They're more than guidelines, but there's something called the IGF code. It's the code for using natural gas on ships. So we use that as a kind of a regulatory basis, but we have to be cognizant of the fact that hydrogen is different than natural gas in some areas, and you have to be careful about that. So what are the safety issues of using hydrogen on a boat? The issue is fire. This is the primary safety issue that you have to prevent. And Ernest, it's kind of a misconception in the world community that hydrogen, it's easy to explode. That's actually not true. It's not true. There's been many studies of this. A.D. Little did some studies in the early, in the 1960s. Stanford Research Institute, SRI, Michael Groth did some studies looking at hydrogen properties and ignition properties, and there have been some beautiful DNVGL experiments done recently in a maritime context where they spilled liquid hydrogen and tried to ignite vapors. What you almost always get is a fire, and there's really three things you need to get a direct detonation with hydrogen, and this is been done by a lot of science. You need confinement. You need hydrogen to be in the right fuel-to-air mixture for an explosion, and you need to be trying to do it. You need a strong ignition source, like a blasting cap. In all other cases, you get fire. Now, you can get accelerations of fire in certain situations, like in tunnels with obstructions, and you can get an acceleration in flame speed with a hydrogen fire that can transit to a detonation. That's called the deflagration to detonation transition. But you can do a lot to engineer that out. By far, and I think a lot of the myth around, or I'd call it a myth, but misconception that it's so easy to explode hydrogen to explode is the Hindenburg. People are always saying the Hindenburg exploded, but it didn't. It was a fire. Now, the fact that it was a fire and not an explosion is little comfort to the people who perished in that accident. About 35 people were killed and about the same amount were grievously injured. You don't want to be in a fire. You really don't. Fires are very dangerous. So the safety issues, but that vessel of the Hindenburg did not explode. And after it's kind of a little part of my quiz I give when I do this hydrogen safety training is I show them a picture of the Hindenburg. I say, was it a fire or an explosion? An explosion is a firecracker. The vessel was burning, and that's just a distinction. But I find, Ernest, that there's a misconception around hydrogen around this question.
Yeah, for sure.
And that drives a lot of the fear around it. But once I explain it, it's like, okay, it's kind of similar to natural gas, which in America, 50% of homes have natural gas in them. This is a flammable gas. And so the precautions are very similar. For using hydrogen on a vessel, you want to eliminate leaks. You really have to do a good job with leak detection. You want to eliminate ignition sources where you think you might possibly have either an intentional release of hydrogen or an unintentional release of hydrogen. And in an indoor space, like where you're using a fuel cell, like say in a fuel cell room, you want to have ventilation in case there's a leak. So here's the approach we take to using hydrogen, say, for example, in a fuel cell room on a boat. When we first started doing our feasibility studies back in 2016, that's now 8 years ago, our time goes by fast. The way you would use the approach to safety for using a fuel cell in an enclosed space, like in a fuel cell room on a boat, would be to have a fuel cell. Usually the modules are in racks. So maybe you have 4 modules put in a rack. So you have these fuel cell racks. The racks are ventilated. So you have a airflow going through the rack from bottom to top. And you also have a hydrogen detector in the rack. So if you detect something, you can shut it down. The rack is in a fuel cell room, which is independently ventilated. Important that it's independently ventilated. And also has its own hydrogen detector up there. So you have sort of 2 levels of defense. Now, this was an approach that the U.S., by the way, to get a boat onto the water in the United States, you have to get through the Coast Guard. This was an approach that the Coast Guard found acceptable. And it's called an emergency shutdown procedure. So if you detect hydrogen anywhere, you just shut everything down. And hydrogen, by the way, I want to mention this, Arnes. This is almost never talked about, but there's a safety feature of hydrogen that is a great advantage over batteries. When you have a battery, like a fully charged battery, if something goes wrong with the battery, all the energy that's stored in that battery, say it's a short somewhere, all the energy that's in that battery is available to the accident. That's why battery fires are so difficult to manage. But in a hydrogen fuel cell, although a fuel cell is very similar to a battery in the sense that it's an electrochemical device that converts a chemical reaction, hydrogen plus oxygen going to water, to energy, the fuel is kept separate. The hydrogen is kept separate in storage tanks, and the oxygen is drawn in through a blower. So if there's a problem in the fuel cell, there's very little energy. There's very little chemical energy in the fuel cell at any given time. So you just close valves off. Okay, that's a real safety advantage to fuel cells over batteries. I just want to mention. But hydrogen has others. It's a flammable gas. So anyway, but the fuel cell so getting back to this fuel cell room example, the fuel cell companies have done a pretty cool thing. There's been the fuel cell companies, and Ballard is one that comes the most directly to mind, has made the safety of fuel cell use on a boat even better. And what they've done is they made the fuel cells such that I'll have to be a little obtuse in the sense of, or obscuring of technical details, but they've made it such that if somewhere in the stack you get a leak, that is in the fuel cell stack assembly, you get a leak, the fuel cells are now self-contained in such a way that there's no direct path for that hydrogen to get out into the room. Instead, it's channeled out, usually ultimately through a vent mass on the vessel. So the fuel cell company, in Ballard in particular, has made a very nice technical advance in using hydrogen safely in an enclosed space on a boat. And the driver for doing this is that by doing this, you relieve some of the requirements on that room. By making that an inherently gas-safe room, it lowers the ventilation requirements on the room. It allows you to put more things in the room that you could otherwise, if gas could potentially get into the space. You don't have to have an airlock on the room. So there's some structural things which are good. But I mentioned RNS, that the hydrogen eventually gets vented out through a vent mass. So all hydrogen vessels have a vent mass. This is the pipe. Currently, it's a pipe sticking up in the air. Natural gas vessels also have this. Natural gas, which is mostly methane, is a lighter than air fuel. So they also have vent mass. So a key feature of safety for a hydrogen vessel, using a hydrogen vessel, is this vent mass. And in the webinar, I'll show some examples of that, of how we use vent mass on the boat. For using hydrogen, in most of the boats, we'll be using liquid hydrogen just because the amount of hydrogen is so large in boats. And that's also a cool thing, RNS. In some of the feasibility studies we've done, a single ferry, a hydrogen ferry that we looked at back in 2016, would use the equivalent of 2,500 light-duty vehicles, fuel cell vehicles. These ships use a lot of fuel because it's so hard to move a boat through water. You're pushing this big thing through this very resistive stuff called water. That takes a lot of energy. That means you got to put a lot of hydrogen on the boat. So that's a great thing about boats, because it's such a great application because it uses a lot of hydrogen, which brings the economies of scale into play. And I digress from safety a little bit, RNS, by telling you one thing. Back in 2016, when we were looking at the feasibility of hydrogen ferries, and I'll talk more about this in the webinar, we asked one of the gas companies, I think it was Air Products, but we also talked to Air Liquide too, and Linde back then. Well, if we wanted to get from you 2,500 kilograms a day of renewable liquid hydrogen, could we get it from you? Because we want these boats to be running on renewable hydrogen. And they said, this is what they told me. They said, Lenny, if we had one customer that was demanding 2,500 kilograms a day of renewable liquid hydrogen, it would change the way we thought about renewable liquid hydrogen nationally in the US. If we just had one customer, one reliable customer that every day was demanding this, it would change the way we thought about it nationally. And this was a maritime application. And why would it change it? Because there was so much hydrogen involved. 2,500 kilograms a day. So anyway, so getting back to safety, for having liquid hydrogen tanks out on the deck, and by the way, there's no Coast Guard regulation about putting liquid hydrogen tanks in the interior of a ship. There are absolutely none. In fact, some LNG vessels have their LNG cryogenic tanks in the interior of the hull. There's no restriction around it at all. But in the studies we've done, and again, these will be in the bibliography section. It's just sort of natural to put them at what the maritime people call out in the weather. So out in the weather means it's just outside on the boat, and there the safety issues are managed. The concerns are leaks, like small leaks of liquid hydrogen, which become, as it expands because it warms up, hydrogen leaks. So there the concern is fire. And the way it's approached in maritime, in the implementation of liquid hydrogen, you don't have to do this, but it's a way to help control it, is to put something called a tank connection space on these liquid hydrogen tanks. And they're in a tank connection space, it's just kind of like a box around all the hardware that comes out of a liquid hydrogen tank. If you ever look at the end of a liquid hydrogen tank, there's all this hardware coming out of the end caps. There's tubes, all kinds of stuff. And you just put that in a ventilated box. And so that if there is a leak, it happens in this ventilated box, which is inerted. Usually it's using like pure nitrogen. So there's not, you can't get a flammable mixture in there. And then the vent, the exhaust of that box is routed up the vent mass. So, the overwhelming primary concern around safety RNS is fire. You have to prevent fire. And if you prevent fire, you prevent everything else. Any other like deflagrations or transitions to possibly a detonation, a DDT, prevent fire. And that's what it's focused on, because that's the thing you don't want to be on a boat in a fire. You don't want to be in a fire on a boat. Either one of those applies. You do not, there's no place to go. And that's why RNS, the safety regulations for ships is much more stringent than in almost anything else I've seen, because there's nowhere to go.
So how do hydrogen's properties affect safety protocol design?
How do hydrogen what?
Hydrogen properties affect safety protocol design.
Yeah, it's very interesting. Usually what you end up having to deal with, even if you have liquid hydrogen, is you have gaseous hydrogen as a fire risk. And it's for the most part, it's okay. You can use the liquid natural gas regulations. It's very buoyant. Hydrogen is really buoyant. It's much more buoyant than natural gas. If you have if you imagine this, Arnes, if you take liquid hydrogen and just take a small amount of it and leak it, right? So you're not dramatically changing the temperature of the environment. That hydrogen will become more buoyant than air, just with a temperature increase of 2 degrees. So if you take 20 Kelvin liquid hydrogen and just squirt a little bit of it into the air, as soon as that hydrogen gas, it'll get warmed up by the air molecules, right? As soon as it gets just 2 degrees more than 20 Kelvin, 22 degrees, it becomes more buoyant than air. That for natural gas, you have to heat it up. The natural gas, if you do the same thing, if you squirt it into, take a little bit, squirt it in there, it has to warm up by 50 degrees to become more buoyant than air. So hydrogen is extremely buoyant. The other physical property of hydrogen, and this is an area where we're engaging with the Coast Guard somewhat, because if you're properly handling a leak of hydrogen, you're venting it out through the vent mass, say. If it's coming out that vent mass, it's going straight up, 45 miles an hour. But yet the current regulations require a spherical exclusion zone at the top of that vent mass, because they're worried about hydrogen somehow getting down. But we've been trying to tell them that unless you have wind blowing straight down, which never happens, wind is always blowing horizontally. Even if you're near a building, can be downdrafts, but those downdrafts have weakened velocity. It's pretty hard to get, the gas is so buoyant, to get it to go down. So we've been arguing that the specific property of hydrogen, that it's highly buoyant, should only require a hemispherical exclusion zone at the top of that vent mass, like a space above the vent mass, as opposed to having to extend all the way down. But the current regulations are it has to extend all the way down. So far I've been unsuccessful in that. But it's extremely buoyant, which is good for safety because it means it disperses quickly. That's a good thing. And by the way, I wanted to mention that a leak of hydrogen is not an environmental issue, because hydrogen is not a direct greenhouse gas. It's inactive in the infrared. So a hydrogen molecule is not a greenhouse gas. That's an environmental safety issue. It has some photolytic properties in the atmosphere, but molecular hydrogen, if it gets to the upper reaches of the atmosphere, will eventually leak into space. So that's one of the reasons there's not a lot of hydrogen in the atmosphere, is that it has escape velocity. So if it gets up in the atmosphere, it can leak. So anyway, but some of the things around hydrogen are some of the properties of it which drives safety is that its flammability range is quite wide. The lower flammability limit is about 4% mixed with air. The upper flammability limit is 75%. The corresponding numbers for methane, which is most of what natural gas is like 5 to 13%. It's much narrower. And because so what does that mean? What that means is that in a leak scenario with hydrogen, the physical properties are such that if it encounters an ignition source, it's going to burn. You won't get lucky enough. In natural gas, because the flammability range is so narrow, and in an accident, it's kind of a random mix. It's whatever it produces. The chances are actually in a natural gas scenario that if you happen a random mixture of natural gas and air, even if it encounters an ignition source, won't ignite because the flammability range is low. So you're probably out here somewhere. With hydrogen, that's not the case. So you really have to do a good job eliminating ignition sources, because if there is a leak and it's not contained, like in the newer fuel cell designs, or it's not contained because somehow it gets out of a tank connection space, which I described earlier. The mixture there is likely to be in the flammable range, and if it encounters an ignition source, it will burn. So that's a kind of a peculiarity of hydrogen that drives a safety awareness around it. But there are other things too, like in liquid hydrogen. You don't want to physically encounter liquid hydrogen. There's the safety aspects of hydrogen that are based on its physical properties are really interesting. Flames of hydrogen, like if you do get a fire, flames of hydrogen are very hard to see because there's no carbon in them. The flames aren't colored. So they're hard to see outside, like on a bright sunny day, because they're kind of a light colored blue. So you have to do, I think, a good job with fire detection, infrared detectors, and so on. But interestingly, hydrogen fires don't emit a lot of thermal radiation. So if you do have a hydrogen fire, it's heating structures around it much less, like by a significant amount. And the reason for that is because there's no soot in the flame. It's only water. So the radiative emission properties of water are much different. And so if you have a hydrogen fire and it's just like it'll be a tall fire because it's buoyant. It'll heat structures less, which is a good thing. The water in the atmosphere, this is interesting, Ernest, because water is the product of a fire with hydrogen plus oxygen going to water, and water in the flame is what's doing the emission. If you have air outside of the flame, the water molecules are excited. It's not a perfect match of a radiative infrared absorption, but the water in the air will absorb hydrogen radiation coming from the water in the flame, absorb it, and then re-radiate it everywhere, which means that in a direct line of transit, just normal humidity will knock down radiative heat from a hydrogen fire quite a bit, like 30% in 4 meters is kind of the number. So there's some very interesting physical properties of hydrogen, which in accident scenarios produce different results. The fires are less radiative. If you spill a lot of liquid hydrogen somewhere, liquid hydrogen evaporates so quickly. If you look at liquid hydrogen cross-eyed, it'll evaporate. The enthalpy of vaporization is so low that if you spill like 1,200 kilograms of liquid hydrogen on the ground, it'll evaporate completely in 6 seconds. So whatever's going to happen happens fast. So that's really interesting. The liquid natural gas spill is also a pretty short duration, but 4 or 5 times longer. The fuels hang around. But if you have a diesel spill, like in a vehicle, the diesel spill stays there a very long time and is available to the accident. So I'd say the physical properties are very interesting. Easy to evaporate means spills or liquid hydrogen are very short duration events. The flame properties are interesting. The hydrogen fires produce less infrared emission, heat emission out of them, and that's a good thing because you heat structures less. It's highly buoyant, which means it disperses quickly. And another thing I want to mention, RNS, is because I've been doing so much work with hydrogen in maritime environments, we get this question, a good question occasionally, that is, well, what happens if you have a hydrogen leak and it gets blown under a pier? Is it like we'll just stay there? What happens then? Do you just fill up the bottom of the pier with hydrogen? And these are good questions, I think. Well, the answer is that no, you don't do that. And the reason is that there's another property of hydrogen called diffusion, which means that if you imagine putting like a little bit of hydrogen in the center of a box and it's completely sealed, so no air moving, nothing, the hydrogen will just slowly diffuse. It's like dropping a drop of oil in a bucket of water. The oil will diffuse, and if you drop a drop of oil in a river, it'll also diffuse, but the river will take it away, right? But if you have a situation where you think hydrogen might get trapped, hydrogen diffusion, which can occur over hours, will make that hydrogen just go everywhere, and eventually, whenever it gets away from under the pure structure, it'll just go up into the atmosphere. So hydrogen diffusion, the strong tendency to diffuse in air, makes it, argues against it collecting in structures like piers where it eventually could get out. Piers are kind of open on the sides. It doesn't help you in a sealed parking garage, though, but in that case, you have to have ventilation. But diffusion keeps you from long-term accumulation. Buoyancy disperses it quickly, gets rid of it. And low enthalpy of vaporization for the liquid means that spills are very short-term events. They're not around very long. And but the wide flammability range means if you have to really prevent leaks, which you want to do anyway, and be monitoring them properly. And especially on a boat, you want to have like IR monitors for looking for heat excursions, which can be a signal for fire.
Lenny, I think this interview could go on forever because it's so interesting.
I have time.
Let's look at the hydrogen in aviation. You said you worked with Boeing.
Yeah, so this is something. Do I actually have this book? I think I might have this book. I got a book for you, Artis. Can you see that?
Yeah.
Okay. Anybody who's interested in hydrogen uses in aviation need to get this book. It's written by G. Daniel Brewer. Can you see that?
Yeah.
So this book was written in the 1990s, and we can put that in the bibliography too. So Lockheed, back when Lockheed was making commercial aircraft, the older people in your audience may have heard of the Lockheed L-1011, which was a very nice commercial aircraft. Lockheed did a lot of work looking at hydrogen in aviation, and G. Daniel Brewer was the head of Lockheed's hydrogen program for aircraft. And what drove that interest back then was if you could take advantage of how light hydrogen is as a fuel and make it used to provide propulsion power for an airplane, because hydrogen will burn in an engine, in a turbine engine. Hydrogen plus oxygen goes to water and it releases energy and it gets hot, and that hot makes it get blown out the back. So they did a lot of work. So that book was written in the 1990s, which was a summary of the work they did in the late 70s and early 80s, where they developed designs for commercial aircraft that took advantage of liquid hydrogen, because that's still the most dense way to store it. But remember this factor of 4 increase in volume, Arnes, I mentioned? Yeah. That there doesn't seem to be a way around that. So the question is, can the aircraft frame tolerate that factor of 4 increase in volume? And the answer is yes, it can. But the weight savings could be huge. Like you could use 25% less fuel in a commercial aircraft in some of their designs. Boeing has also done some work in this in the 90s. There was some work by Boeing done, and Airbus has done work as well in the early 2000s. They called it a cryoplane. And I've done work in it myself. The work I did with Boeing, which was actually the very first project I did in this market transformation thing I told you about in my introduction, was Boeing wanted to get some, this was back in 2005, Boeing wanted to get some experience with hydrogen. And they said, well, let's just do the simplest example. We don't want to worry about powering the airplane, but let's just see if we could maybe introduce it onto the airplane in some way. And so in airplane design, there's a lot of fighting over like who gets what space, and it's really interesting. But anyway, we looked at an emergency power system for a commercial aircraft. This was back in 2005. And it was meant to be a replacement for something called a ram air turbine. So a ram air turbine is a propeller. It's like a little propeller that's housed underneath the wing of an airplane. All airplanes have this. And if the airplane loses all electrical control, like all electrical power generation, that is the generators and the engines, and the engines are generators for electricity. If you lose everything, what this ram air turbine is it flips out into the airflow and the propeller starts spinning. And that gives you enough power to get the plane on the ground. It can't, in a glide mode, it allows you to have navigation electronics and kind of key electronic control of the aircraft, but not propulsion control. So we looked at replacing that thing with a fuel cell. And it turns out you could replace it with a fuel cell, and we worked out how you would do that. And then the project, and we wrote a final report on it. I don't know if we published it. I don't think we published it, but we wrote a report on it, which we could also put in the bibliography if people are interested. And then Boeing was more, and this all started with Boeing. And we also did another project with Boeing, it's funded by DOE now, because the DOE was starting to get interested in this. And so in the late 2009 timeframe, we did a study looking at using hydrogen fuel cells to power what we call auxiliary power on an aircraft, like galley power, in-flight entertainment power, non-propulsion power levels, things for an aircraft. And we worked out how you would do this. We wrote another paper on this, which has actually gotten a lot of attention. It's been pretty highly cited, so people are kind of interested in this topic. We'll put that in the bibliography too. We also did some work with Boeing in ground support equipment. We were talking with Boeing. They said, well, it's hard to get new technology on an airplane. People are fighting. There's a lot of turf. People are guarding their turf. We want this. We don't want to give you some of our weight budget. It's really fascinating. But they said, well, what about in ground support equipment? Maybe we could build something. So we built a fuel cell powered lighting stand, which is used often in ground support equipment. And this is a chance to introduce hydrogen technology into equipment that Boeing uses, or the end users of Boeing aircraft use in their management of the aircraft, like for maintenance and so on. So we built 6 of these things. They were high pressure hydrogen, 350 bar storage, and used lights. They're kind of like replacement for diesel generated light towers that you may see like at a soccer game. Schools may deploy them, or construction sites. So we use these as a way of just kind of seeing how it all went together, but also to allow end users to really use hydrogen technology in aviation. So we had 2 of these at the San Francisco airport, and they're still being used. As far as I know, they were being used as of 2 years ago, even though the project ended in 2014, where they use them for maintenance, aircraft maintenance, for doing runway repair. And that's allowed San Francisco airport to get experience having hydrogen delivered to them, high pressure gas. So they started to get a feel for it. Interestingly, in this book, the Hydrogen Aircraft Technology book this is how great this book is. They did a study, Lockheed did a study of how you would convert San Francisco airport to an all hydrogen facility for both propulsion power and ground support equipment. So
Wow.
I would like to acknowledge the people who went before, because the people who went before did a lot of good work. So, and these fuel cell mobile lights allowed it was an interesting project. again, we wrote a paper on it. I'll put it in the bibliography. It allowed us to also put these things in the hands of construction crews, like at the California Department of Transportation. They got some experience using hydrogen via these very simple devices that they used in, for example, chain control up in the Sierra Mountains, where they needed a light to check people, to make sure people had the chains on their tires. And in aviation, we used it. We also used, interestingly enough, Arnaz, we used it in the entertainment industry. So we used these mobile lights. We showed these mobile lights to Paramount Pictures in Hollywood. We did a demonstration for them because it turns out they're also interested in clean power. They use diesel generators a lot in all of their remote shoots. Diesel generators are loud. They're polluting. People don't like them. So they like the fact that these were zero emission systems. Again, this all came from this aviation project, right? It's an aviation project. They also like that they're quiet. And that's something I haven't mentioned about fuel cell technology yet, but it's pretty quiet. It's much quieter than diesel technology. So these units, it turned out we use these units on the red carpet at the Academy Awards. So at the Academy Awards, the Screen Actors Guild Awards, and at the Emmy Awards, we had mobile light, hydrogen fuel cell mobile light technology coming from a Boeing project on the red carpet of the Academy Awards, and I got to be in one of the guys from the fuel cell company. We're actually on the red carpet of these awards shows. It's pretty fun experience. I have to say, I like my community. I like the science community, so I'm happy there. But it was a fun experience. So the aviation application in this case, Arnaz, is for propulsion power. It's pretty compelling if you use a lot of hydrogen, like in commercial aircraft, long-range transport aircraft. But for small applications like fighter aircraft, accommodating the 4x increase in volume makes it difficult. It would cut into the like fighter jet performance. That's kind of harder to see. The benefits are smaller because those don't use much fuel anyway. But there is some application in very high-speed aircraft, like hypersonic aircraft, just because the fuel's so light. In fact, some of the earliest hypersonic aircraft designs use liquid hydrogen as a fuel source. So because it's light. A little bit of a long story there, but thank you for bearing with me.
Definitely a great story. A lot of the facts that I didn't know, but I assume a lot of the audience didn't know. And finally, I think we will almost hit the 2 hour mark, but it's so interesting. So the final question would be your take on the current state of fuel cells.
So I think fuel cells have made a tremendous advance in the past 10 years. And I've seen this firsthand. I'll tell you about it through a project that we did on us. Back in 2014, Sandia led a project. I wasn't the project lead on this, although I was involved later. Joe Pratt from Sandia led this project, and it was to build a 100 kilowatt containerized fuel cell system. So this was a containerized system that was in a 20-foot shipping container. So the dimensions were 20 feet by 8 feet by 8.5 feet, something like that. 100 kilowatts. It had hydrogen tanks in there, had all the power electronics that you needed. And you could just pick this thing up and put it wherever you wanted and have fuel cell power. And this was very useful for people at ports because it's very expensive to get new power into a port location. It takes a lot of infrastructure. It's very expensive. And they kind of like the idea of, wow, you could just get this thing delivered to you and it could provide 100 kilowatts of power for, 11 hours before you need to refuel it. So getting back to the fuel cell, that project came to a conclusion last year, and this is a project funded by the Department of Energy and the Department of Transportation's Maritime Administration. By the way, Arnaz, I'm going to take a little tangent here before I go back to the fuel cells. The people at these funding agencies never get any credit. that is the people at the Department of Energy, and Pete Devlin is the guy who's funded me mostly. You have to have somebody there who's willing to see it, to see like the value of something, to see the need and fund it. The same is true with the Department of Transportation's Maritime Administration, which funded all of my hydrogen work, hydrogen vessel work, which I'll talk about in the webinar. Brian Vogel, Sujit Ghosh, Michael Carter, and Dan Yuskett, Marad, have been very supportive, and you need these people to see it, because sometimes they're competing with other desires within the funding agencies to get something. And so I want to acknowledge those guys that I just mentioned. They never get any credit, and I'm trying to fix that. So thank you, RNS, for letting me take a little diversion to get these people the recognition they deserve. I'm trying to do it in all my presentations too, that they're just as important as anybody else, and they never get any credit. Anyway, going back to this fuel cell generator project, we want to do some other different version of it. But back then in 2014, 100 kilowatt was the best you could do. The power footprint for fuel cells has quadrupled in 10 years. So in the same space, we could now consider putting a 400 kilowatt fuel cell unit. That's an amazing increase in power in the same footprint. And the fuel cell companies deserve a lot of credit for this. So now when we're thinking about how would we use this at a port, we can start to consider a lot of different types of things. Initially, we were thinking about just providing hotel power for a boat that might be there. But at 400 kilowatts, you can start to consider powering a lot of different things. So I think the reliability of fuel cells, the lifetime of the fuel cell stacks has gone up. The power density has gone up a factor of 4. And I'm talking about PEM fuel cells because in mobility applications, it's typically a PEM fuel cell that you're talking about because of the fast turn-on time, their quick response in mobility that is on ships or using it on a car. For station applications, there are other types of fuel cells: solid oxide fuel cell, phosphoric acid fuel cells. My comments are about PEM fuel cells, proton exchange membrane fuel cells. So. The lifetime of the cells has gone up quite a lot. I think back in 2014, the lifetime was probably 10,000 hours maybe, but I think it's certainly into the 20,000 hours now, and even higher probably. So doubling of the lifetime, quadrupling of the power density. I mentioned before that some of them are now being self-contained, so you can't have hydrogen leaks out of them directly. I mentioned that in the fuel cell room application. There's been, I think, tremendous development of this PEM fuel cell technology. A lot of it was driven by the light duty car application. Toyota did a lot of great work reducing the footprint of a 75 kilowatt PEM fuel cell power plant that you would want to use in a car, and getting that to fit in the space under a hood. The Toyota work on decreasing the footprint, and they're now making available fuel cell PEM power generators which leverage all that great work they did. That's just been an amazing accomplishment in terms of footprint. So compared to what this project we did starting in 2014 to what it is now, I mean, we have to really, the improvement in PEM fuel cell technology has been, I think, remarkable. And the companies doing the R&D, the national labs doing R&D work in that, and private and academia deserve a lot of credit for that improvement. I think it's been really remarkable. I'm less familiar with the other types of fuel cells. I'm mostly involved in mobility applications. There could very well be similar improvements in solid oxide fuel cells and phosphoric acid fuels, but I haven't seen it because I'm just not exposed to it.
Lenny, thank you very much for this great conversation. I'm really looking forward to the webinar we're going to have. And for all the viewers out there, it's going to happen on May 22nd. And the main topic is hydrogen fuel cell technology for ships, from feasibility studies to first hydrogen vessels. Prepare your questions and be ready for this one. It's gonna be awesome. And it is going to happen 5 p.m. CET, that means that a lot of people globally will be able to watch this. Lenny, thank you again for being my guest today.
It's my pleasure, Ines. I look forward to it. We'll get together the papers for the bibliography for this
Definitely,
interview.
everyone, you will have a chance to see all the links to the papers and to check them out. Thanks again, and until the next time.
Thank you, Ines.